let's talk about the basic properties of the integers. As with the natural numbers, we won't take a strict axiomatic approach to the integers. Instead, we'll just note the highlights. Our goal is to state a unique factorization result for integers into primes. Now, we have the integers. Okay, so the notation is z. We form the integers by taking the natural numbers, we include their negatives, and we include 0. So our picture looks like this. Okay, the integers sitting in the real number line. As with the natural numbers, if I want to define addition, we can think of that as repeated application of a successor function. If we want to define subtraction, that's repeated application of a predecessor function. With predecessors and successors, we can put a total ordering on the integers. Okay, we call that less than or equals to. Now, this business of predecessors and successors, for the integers, every integer n has a unique predecessor, n minus 1, and a unique successor, n plus 1. We note every positive integer can be brought down to 0 by repeated application of predecessors. Every negative integer can be brought to 0 by repeated application of successors. Now, that's addition and subtraction. We also have multiplication. Okay, so we can bring in the multiplication from the natural numbers. Now, if I have m greater than 0, okay, we define m times n just as taking n added to itself m times. Okay, so this will work for negative integers and 0 also for n. To get to work when m and n are both negative, we'll say that minus 1 times minus n is equal to n. M times 0 is 0. Now, with the addition and multiplication, okay, we'll have a list of properties. So we'll have associativity for both operations. We'll have commutativity for both operations. Together, we'll have a distributive law. And then a useful function will be absolute value of an integer. So if our integer is in the natural numbers, union 0, we just get the number back. If we get a negative integer, we take away the minus sign, which is just the same as multiplying by a minus 1. One important property for us, under multiplication, the integers have no 0 divisors. So this means if I take m and n integers, multiply them together and get 0, that either m is equal to 0 or n equals 0. So if 0 comes out of a product, that means 0 had to be going into the product. Now with this, we get the cancellation law for the integers. So if we take a non-zero integer m, we have mx equal to my, then that forces x to be equal to y. So when we have these conditions, we could just cancel off the m's. Now to see this, okay, if mx is equal to my, I move everything to one side and then I factor out the m. So that gives us m times x minus y is 0. So either m is 0 or x minus y is 0. By assumption, m is not equal to 0, so we have to have the x minus y is 0 or x is equal to y, and that's our cancellation law. Now, still working with multiplication, okay, we're also interested in division. So we have long division for the integers, okay, so we'll assume that m is not equal to 0, m and n are integers, then there exists a unique integer r between 0 and the absolute value of m minus 1, such that n is equal to k times m plus r. So this is just our usual long division. I take n, I divide by m. Either it divides evenly, or there's going to be a remainder, and that remainder is what we're calling r here. Now, okay, just for definition's sake, if r is equal to 0, then we say that m divides n. Okay, so we have m bar n. And that just says there exists some k in the integers, such that n is equal to m times k. So that's our definition of division. Let's show that we always have a remainder in the desired form. So our remainder is always between 0 and absolute value of m, including 0. We'll start by forming the subset of the natural numbers, union 0. So what I'll do is I'll take all integers of the form n minus k times m. K ranges over the integers, but we want that these numbers are greater than or equal to 0. by the well-ordering property of the natural numbers. This set has a least element, so we'll call that R. I want to show that R is between 0 and absolute value of m, including 0. Now, it won't be less than 0, okay, just by definition. So what's going to happen if R is outside of this range? Well, that means that we'll have to have the absolute value of m is less than or equal to R. We can subtract off the absolute value of m for both sides of that inequality. That'll give us 0 less than or equal to R minus the absolute value of m. Because absolute value of m is 0 or positive, that means this difference is strictly less than R. Now, because this number is greater than or equal to 0, it's inside of our set S, but because it's strictly less than R, that means R is not the least element of this set. So we get a contradiction. So that means R is going to be in the desired range. Next, we have the analog of, okay, if we're showing two sets are equal, we'd show mutual inclusion. So if I want to show that two integers are equal, we could do that by showing mutual division. But then we'll get equal up to a plus or minus sign. So we have m divides n divides m. The m is equal to plus or minus n. So we get this just by following the definitions. So if m divides n, we have m equal to kn for some integer k. If we have n divides m, we have n equals lm for some integer l. String our equalities together, I get m equals to kl times m. And I can use our cancellation law to cancel off the m's. So I'll be left with k times l is equal to 1. Now, the only way we can have k times l equal to 1 is if we have k equal to l and they're either both 1 or minus 1. So that gives us our test here. Next, definition. Okay, we have the greatest common divisor of integers m and n. So we're going to assume that m and n are both non-zero. The greatest common divisor of m and n is going to be a positive integer. It satisfies the following two properties. We'll have that greatest common divisor of m and n divides m and n. So it's going to divide both m and n. And we have if d divides m, d divides n, then d must divide greatest common divisor of m and n. So greatest common divisor to divisor, and among all divisors, it's going to be the greatest in terms of division. Let's check that this definition makes sense. So we want that a greatest common divisor exists, and if so, that it's unique. We do uniqueness first. So let's suppose we have two greatest common divisors of m and n, g and g prime. If we check condition 2, then g divides g prime, and g prime divides g. By our previous result, that means that g is equal to plus or minus g prime, but because they're both positive, we have to have that g and g prime are equal. So uniqueness. For existence, we'll use proof by induction. Now, we'll assume that m and n are positive integers. Our induction is going to be based on k equal to the maximum of m and n. For our base case, k equal to 1, we have the stronger statement that if I take greatest common divisor of 1 with any positive integer, we get 1 back. So that's our base case. For the induction step, we suppose greatest common divisor of I and j exists when the maximum of I and j is less than or equal to k. Or just I is less than or equal to k, j is less than or equal to k. I want to show that same statement with k replaced by k plus 1. Now, we pick an I and j, satisfying this condition. Then we have two cases. If I and j have no common divisors, then their greatest common divisor is going to be equal to 1. And then we're finished. Otherwise, there's going to be some divisor greater than 1. So that means I'll have I prime equal to I divided by d, j prime equal to j over d, given as integers. These satisfy the condition, okay, I prime and j prime less than or equal to k. So that means there exists greatest common divisor of I prime and j prime. So we'll call that g. Now, if we check g times d, That satisfies the conditions of 1 and 2, and that's going to be greatest common divisor of I and j. So that shows our induction proof, and thus we have existence. As a special case, we have the following definition. For non-zero integers m and n, so that m and n are relatively prime or coprime, if and only if the greatest common divisor of m and n is equal to 1. So that means m and n have no common divisors or factors. Next, we have Bezout's identity. So this is going to give us a way to relate the greatest common divisor of m and n to m and n in a single equation. So if m and n are non-zero integers, then there exist integers j and k such that j times m plus k times n is equal to the greatest common divisor of m and n. To see this, first we can assume that m and n are positive integers, and we'll have that m is strictly less than n. We can divide through our equation on both sides by the greatest common divisor of m and n. That lets us consider m and n that are relatively prime. So we'll just assume that. Now, I'll consider the set S given as all combinations jm plus kn, where j and k are in the integers. Because m is positive and strictly less than n, we just apply long division. So I can say that n is equal to lm plus r, and I'll have r strictly between 0 and m. Greatest common divisor of r and m is equal to 1. Now the reason we have that, if m and r had a divisor greater than 1, it would also be a divisor of n. And then we would have that m and n are not relatively prime. That divisor would divide both of them. Now you'll note the conditions we have here are the same that we have for m and n. So what we're going to do, I'll replace n with lm plus r. When we put it in here, I can collect all the m terms to get s represented as all combinations jm plus kr. Now we're going to repeat that process again. We'll have m where we had n and r where we had m. We keep repeating. The remainders are going to keep being driven down to a strictly smaller number, but always positive. So eventually we're going to push the remainders down to 1. Once I have that remainder equal to 1, we're going to have all integers in our set. And so somewhere there's going to be one of these combinations equal to 1. For a concrete example, consider m equal to 5, n equal to 7. These numbers have no common factors, so the greatest common divisor is equal to 1. If we work the numbers a little bit, we arrive at the solution minus 4 times 5 plus 3 times 7 equals 1. So Bezout's identity checks out. Of course, you should work enough examples until you're convinced that it works. Now, definition, integer p greater than 1 is called prime if and only if, whenever d is positive and d divides p, implies d is equal to 1 or p. So this just says d has no proper divisors. Now, this agrees with our usual notion of prime, so that would be examples 2, 3, 5, 7, and so on. Next, we have a proposition. So if the greatest common divisor of m and n is equal to 1, with m divides n times x, then we have to have the m divides x. So the way to think of this, because m and n have no common factors, all the factors of m have to go to x. We see this using Bezout's identity. So, because of the division, there exists some k such that n times x is equal to k times m. Using our identity, there exists I and j such that I times m plus j times n is equal to 1. We'll multiply through by x and then put everything on the other side. So I'll have that jnx is equal to x minus imx. Now, we have this here. That's going to be the same as if we multiply this top equation by j. So this is equal to jkm. I push the imx to the other side, and we know it. We have x equal to m times another integer. So that means m divides x. So that's our result. Now, corollary, if p is a prime and p divides the product n1 through nk, p divides at least one of the ni's. So this is just going to be an application of our proposition. Okay, it's a straightforward induction, so I leave it to you. We now have enough to show our main result. Unique factorization of integers into primes. It's a statement. Every integer n greater than 1 factors uniquely into a product of powers of primes. Two parts to this. We have existence and uniqueness. So, existence of the factorization says I can write n as a product. Okay, the p's are primes. So we have p sub 1 to exponent I sub 1 through p sub k to the exponent I sub k. Then we have uniqueness. So if we try to write this in a different way, say n equal to q sub I j sub 1 through q sub l to the j sub l, where the q's are primes, then we must have each p occurs as a q, and when we identify these, their exponents have to match. So uniqueness. Now, we'll show the existence part. Then the uniqueness is straightforward. So for the existence, we show it using induction on n. So for our base case, we have n equal to 2. 2 is a prime, so it's its own factorization. For the induction step, we'll assume that there exists a factorization when n is equal to k, and we'll show that there's a factorization when n is equal to k plus 1. So there are going to be two cases here. If k plus 1 has no proper divisors, then k is a prime, and there's only one factor, and that factor is k plus 1, and we're done. Otherwise, k plus 1 is a proper divisor d. I could write k plus 1 as d times j. We'll have that d and j are strictly between 1 and k. So our induction hypothesis applies to both d and j. So I could write those as products of powers as primes. We combine, and we get our factorization for k plus 1. So that's existence. For the uniqueness, okay, that's going to be straightforward. We're just going to apply the corollary, and we can do that using induction to get our argument. So I'll leave that to you. For our last section, we define and describe properties of modular integers. There are two ways to think of these. First, we could think of modular integers as a way to add and multiply on a clock with n labels. On the other hand, when we divide integers by some fixed integer n, the remainders add and multiply nicely. So modular integers are going to be a way to capture that addition and multiplication just through the remainders. Now, everything starts with an equivalence relation. So we're going to fix positive integer n greater than 1, and our equivalence relation is going to be, it's on the integers, we said j is related to k if and only if n divides j minus k. So one way to say this, we'd say that j is equal to k modulo n. And what this really says is that j is equal to k plus ln, or j and k have the same remainder upon division by n. So we noted that earlier. Now, to show that we have an equivalence relation, we're going to show reflexive, symmetric, and transitive. For reflexive, okay, we'll show j is related to j. So if we take the difference, we get 0, and that's the same as 0 times n. So reflexive. For symmetric, we're going to show if j is related to k, then k is related to j. So we have j minus k equal to L times n. We multiply through by a minus 1. And that gives us k minus j equals minus L times n. This says symmetric. Finally, we want to show transitive. So we want to show if j is related to k is related to I, and j is related to I. So we just write things out, see where it goes. So I have j minus k equals ln, k minus I equals Sn. We add down both sides of the equalities. We get j minus I equals L plus S times n. So we have transitive. So that means we have an equivalence relation. Now, we can form the equivalence classes. Those classes are going to give us a partition of the integers. Now, what's in an equivalence class? Well, if we take an integer j, this will be all k in the integers, such that k is related to j, which is the same thing as the set j plus L times n. We've seen before that the remainder for division of j by n is in here. So if we were looking for representatives of equivalence classes, we could use the remainders. So we'll have labels going from 0, 1, up through n minus 1. Okay, now as noted, we have a partition, which means we can write it as a disjoint union of these a sub j's. Okay, as noted, we only need n of these. Now, on the equivalence classes, there's an addition that's consistent with the addition for the integers. So that would be, if I take the class for I, add it to the class for j, that's the same as the class for I plus j. If we think in terms of the remainders, that would say, if I take remainder for I upon division by n, remainder for j, we get the same thing as the remainder for I plus j, almost. Now, the problem is I plus j may wind up being greater than n, so I would just need to subtract off n to get back into the set of remainders, okay, the integers between 0 and n minus 1. Now, what we're doing here precisely, okay, if I take this class and add it to this class, well, the way I'll define addition is just to take elements from one class, add them to all elements in the other class. So we take elements of this form, add them to elements of this form. We get all elements of this form. Okay, so we just take the kn plus the ln and just write that as ln. So we note here, this is going to give us the class for I plus j. Now, if we want to describe it in terms of the remainders, well, then we have to add or subtract n until we wind up back in the set of labels. Now, as an example, we take n equal to 12. Okay, so here I'm going to have 12 equal to 0 in our clock, so it's going to go from 0 to 11. For instance, if we take 6 plus 7, that's going to give me 13. 13 is not in our set of labels, so I'm going to subtract 12, and that's going to give me a 1. So if I take 6 and just move up by 7, we land on 1. We also have multiplication. So our rule is going to be the same as before. If I take the class for I times class for j, we're going to define the multiplication to be the class for I times j. If we're working with remainders, then we're going to take I times j and subtract off the multiples of n until we wind up back in our set of labels. Now, what's happening here? If we take the class for I times the class for j, as with addition, we're just going to define multiplication of sets as just taking all the elements of one set times all the elements in the other set. When we work that out, we won't get an equality here in general. We're just going to get an inclusion. But that's not a problem. We're just going to send this into the entire equivalence class. So this multiplication will be well defined. Now, as we noted before, the rule is you just multiply as usual. Then if you want remainders, you subtract off until you wind up back in your set of labels. So 0 through n minus 1. Now, when we take a look at our addition and multiplication, almost all the properties from the integers are going to carry over for the basic properties. So we have the associativity of addition and multiplication, the commutativity of addition and multiplication, the distributive property. We'll lose some things. We're going to lose the total ordering. Okay, note if we do predecessors and successors, I could start at 0, keep taking successors, and I'll wind up back at 0. So that's going to kill our total ordering. If our n is not a prime number, then we're going to have 0 divisors. So for instance, if we take n equal to 12, then I'll take 3 times 4. That gives me 12, but then that's going to be equal to 0. So 3 and 4 are not equal to 0, but if I take their product, we get 0. So they're both 0 divisors. We see more of the modular integers when we do abstract algebra.